Hello everyone and welcome to course number 7. This is inspection and minor repairs. Course number 7 because there's no course number 6 since course number 6 was the exam number 1 and I prepare my courses to match the calendar for the courses. So today we're going to be talking about forms of corrosion, different forms, different types of corrosion, and propitious areas for corrosion on aircrafts. So let's do this. 7.1 Forms of corrosion. Introduction. There are several forms of corrosion. One of the simpler forms of corrosion is dry corrosion, or as it is most generally known, oxidation or rust. When a metal such as aluminum is exposed to a gas containing oxygen, a chemical reaction takes place on the surface between the metal and the gas. Now for aluminum, 2 aluminum atoms will join 3 oxygen atoms to form what we call aluminum oxide. On steel, 2 iron atoms join the 3 atoms of oxygen to form iron oxide, or what we call rust. Now, iron oxide is on steel, we refer it as rust, and on aluminum, we refer to it as oxide or oxidation. There's a big difference between iron oxide and aluminum oxide. The film of aluminum oxide is unbroken or impervious, and therefore, once it has formed, further reaction with oxygen slows dramatically, protecting the aluminum. The formation of oxide film on the surface insulates the base aluminum alloy from any electrolytes and prevents further reactions with oxygen. Just a note here, somebody asked me what was all the writing on the aluminum that we see, that we work with in lab. In this example here, we can see Alclad 2043. This is the information as to what is the material. Also, the thickness will be printed. This is ink on the aluminum, and it can be easily removed just by using alcohol. Protection provided by aluminum oxide coating is the main reason for cladding, or what we call the Alclad. So Alclad aluminum alloy is used in structural applications. Iron oxide, on the other hand, forms a porous, interrupted film. Since the film is not airtight, the metal continues to react with oxygen and the air until metal is completely eaten away. Now you can see from that picture that this car's hood is slowly returning to its native state of oxide. The best way to protect iron from dry corrosion is to keep oxygen from coming in contact with the surface. This is done temporarily by covering surfaces with oil or grease, or permanently with coats of paint. Now this is why sometimes you get new parts that are bare metal. They will be covered with a film of oil. This is to actually cut the contact with oxygen to prevent any corrosion. This is mainly if you when you buy bearings or something like that, they're always in a little plastic bag and they're soaked with oil, and it's to prevent any contact with oxygen and prevent corrosion or rust appearing on steel parts. Most common forms of corrosion in aviation are surface uniform edge corrosion. We'll see that in detail in the coming slides. Pitting, galvanic, intergranular, exfoliation, concentration cell, filiform, microbial, etc. So in aluminum or on aircrafts, there are several different types of corrosion that can be found. 7.1.1 Surface or uniform edge corrosion. Surface corrosion is the most common form of corrosion and is caused by the reaction of a metallic surface with atmospheric contaminants, which includes the airborne chlorine or sulfur compounds, of course oxygen, and of course moisture. If an area is unprotected metal unprotected metal, is exposed to an atmosphere containing, for example, battery fumes or exhaust gases or industrial contaminants, a uniform attack over the entire surface will occur. This attack of the surface is characterized by electrochemical reaction over the surface only, and it will become like a powdery whitish surface, a constant decrease of thickness over time. Now this can be a serious issue if the actual metal is being eaten away and that the thickness decreases. That would imply that the actual material will not be as thick as it supposed to be. So that can be a real issue for an aircraft. The amount of damage caused by uniform surface corrosion is normally determined by comparing the thickness of the corroded metal with that of an undamaged specimen, and there's different ways to do this. We'll discuss that in the coming weeks. First indication of the presence of surface corrosion are the matte surface. So shiny aluminum will become matte. Then roughening of the surface, and then the frosted appearance. So these are the different steps that will indicate how badly corrosion has attacked the part. Now what you can see on this picture is seat tracks that are used on aircraft for positioning the seats and attaching the seats to the structure. And as you can see in this case here, not only the surface is matte and it's pretty rough, but it has that frosted appearance, meaning this is pretty badly corroded piece. So not to be confused by color or heat discoloration in exhaust parts. Usually you will get some sort of discoloration. Any of you who have a motorcycle knows that the exhaust, even if it's chromed when it's new, it will actually change color, and this is caused by heat, not by corrosion. If these deposits are not removed and the surface protected against further action, the surface becomes so rough that corrosion pits begin to form. Corrosion sometimes spreads under the surface and cannot be recognized either by the roughening of the surface or by powdery deposit. Instead, the paint or plating lifts off the surface in small blisters due to the pressure of the underlying accumulation of corrosion products. The appearance of surface corrosion varies depending on the type of metal. For aluminum and magnesium, whitening of the surface will indicate light corrosion. White powdery deposit, it's moderate, like we've seen in the when we did the first exercise in the hangar, or the first lab in the hangar on the Challenger wingtips. There was moderate to advanced stage, really. So if you have a white powdery deposit, this would indicate a moderate corrosion. Deep pitting with metal reduction, that's an advanced stage. For copper, you will get a greenish finish or a greenish film that indicates the corrosion. Now, this is a picture of my chalet up north, and as you can see, the roof is green. This is because it's a copper roof. Now, when it gets green, it's copper oxide, and this actually protects the metal itself. On steel and iron, you get this reddish film. Now this is iron oxide, so it's the steel or iron that is actually returning to its natural state of oxide. 7.1.2 Pitting. This form of corrosion is particularly insidious, and it's a likely result of uniform surface corrosion that was left untreated. The attack can be limited to small areas or localized pitting and is able to progress very rapidly in depth while the rest of the surface remains intact. The part can be perforated within a few days or weeks without any noticeable weight reduction of the structure. The first true sign of pitting is a difficult to detect white powdery residue. Localized and disorderly attack leads to perforation of the metal. Deep attack with very small loss of mass. Because one of the inspection methods is to actually weight um, a good part to a suspected corroded part. Uh, so by comparing two identical parts, one that is new, one that is not, if the weight is different, we can actually tell that the part is being attacked. Small craters visible when that white powder is removed. That would be one way of actually verifying if the part is attacked with pitting. It increases the risk associated with damage caused by stress and fatigue because it creates voids inside the metal, sometimes very small, but it can actually decrease the integrity of the part and can be very destructive. Attack parts must be replaced. If there's any pitting on a part, there's no real repair for that, so these parts will actually need to be replaced. Now, here's some examples of pitting corrosion. First, on the left, we have the vertical pitting. On the right, we have the horizontal pitting. So we'll start with the vertical. It can be narrow and deep, quite difficult to find during an inspection because the opening sometimes is quite small. Wide and superficial. This is a little bit easier to find. Vertical granular attack. By granular, we mean it's not the entire material that is eaten away by corrosion, but some elements of the alloy. It can be also elliptical. For horizontal pitting, under the surface, now that means a small opening and a larger void under the surface. Undercutting, this is even larger under the surface corrosion, and this will actually be a bit easier to find because the surface will be deformed. The horizontal granular, similar to the vertical, means it attacks parts of the alloy, not necessarily the whole material, but it will chew away the weaker elements in the alloy. 7.1.3 Galvanic corrosion. This common type of corrosion occurs anytime two dissimilar metals make contact or make electrical contact in the presence of an electrolyte. Dissimilar metals meaning different types of metal. For example, in this case, galvanic corrosion can take place when where dissimilar metal skin are riveted together, or where aluminum inspection plates are attached to the structure with steel screws. Now you have steel, you have aluminum, two dissimilar metals. This will actually create a galvanic corrosion risk. Here's a classic example of galvanic corrosion. In this case, we have a stainless steel screw that is in contact with a cadmium plated steel washer. Now you can see cadmium steel plated washer is much more affected by corrosion than the stainless steel. That is why the washer will corrode, but not the actual screw. This example shows corrosion produced by a stainless steel screw causing galvanic corrosion of aluminum. Now the aluminum surface is in contact with that stainless steel screw. These are two dissimilar metals, probably in contact with electrolytes, meaning rainwater, for example. So this picture shows the corrosion resulting from only 6 months of exposure. Now, the way to prevent that would be to have the aluminum covered with some protective film, like paint, for example. Now, this would not occur if you don't have the electrical contact between the two. When metals of the same galvanic grouping are joined together, they show little tendency for galvanic corrosion. But metals of one group corrode when they are held in contact with those of another group. Further apart groups on the chart on the right, the more active the corrosion. In addition, corrosion is much more rapid when the anodic metal is smaller than the cathodic metal. The reason for this is the greater area of the cathode allows for a higher rate of electron flow, accelerating the speed of the reaction. On the other hand, if the corroding metal, the anode, is larger than the less active metal, the cathode, corrosion is slow and superficial. In this case here, we have the cat-plated steel washer, which is steel and cadmium. And we have the stainless steel screw. So in this case, stainless steel will not react as much, but the cat-plated steel washer gets all the corrosion. So whenever two dissimilar metals are in contact, a short circuit is formed, and it's what we call a galvanic circuit. The speed of the attack will depend on which metal are involved and the surface area of the contact between those two metals. For example, in this riveted assembly, the use of dissimilar metals will cause the corrosion of the less noble material. Now, on the left, you have copper plates with steel rivets. Now, the steel being less noble will corrode, meaning the rivets will actually corrode before the copper plates. In the example on the right, you have steel plates with copper rivets. Now you can see the rivets are intact, being more noble, and the steel will actually be corroded. Now on bolted assemblies, it is sometimes possible to eliminate the contact or electrical contact between dissimilar metals by using insulating washers, gaskets, or bushings. So in the example here, you see an bolted assembly, stainless steel plate, we have a carbon steel plate, and we have a stainless steel bolt and nut. Washers are steel. So there's many different types of materials here. So by installing insulating washers and gaskets and bushings, we can eliminate the electrical contact between them, thus reducing the possibility of galvanic corrosion. 7.1.4 Intergranular corrosion. Intergranular corrosion develops at the junction point of metal grains. Chemically speaking, the periphery and the center of the grain are different and can react with each other in the presence of electrolyte. Now, we mentioned already that aluminum that we use, it's not pure aluminum, it's always alloys that we use. For example, 2024 is with copper, so it's an alloy of aluminum with copper. This means that we have two different metals in contact with each other, because we mentioned also that metals, when we melt them together, they don't actually mix together. They will keep their properties, meaning you have different types of metals that are in contact with each other, basically like what we saw in course number 5, if I'm not mistaken, with sand. The example that I gave with sand, if you have white sand and black sand, if you mix them together, you'll get gray sand when you look from far, but if you look closely, you will still see the white and black grains. So this creates this dissimilar material or metals situation within the actual aluminum piece, for example. The presence of this type of corrosion is almost invisible to the naked eye, but affects considerably the mechanical strength of the metal, gradually destroying the cohesion in the material. Now, this means it kind of turn into dust. So the material is, the integrity of the material is greatly affected by this type of corrosion. It is often the result of impurity in the alloy, and extruded or processed aluminum alloys are at high risk. Under certain conditions, the seams of the grain are the site of the very important localized corrosion, while the rest of the material is not affected. The alloy disintegrates and loses its mechanical properties. This type of corrosion may be due either to the presence of impurity in the joints of the alloy or to local enrichment or depletion in one of the constituents of the alloy itself. 7.1.5 Exfoliation corrosion. Exfoliation corrosion is an advanced form of intergranular corrosion. It is characterized by the raising of the upper layer of the attack metal, or metal will separate into scales. Lifting is caused by the expansion force of intergranular corrosion beneath the surface. It resembles a millefeuille, and I don't know if you like those, but I actually love them. This type of corrosion generally happens in the vicinity of bolts and rivet holes. This type of corrosion particularly affects extruded aluminum parts and forgings, where the microstructure of the grain is highly stretched. Now, in the assembly and installation course, you probably heard about extrusions, and this is actually what you used to create the angle brackets on your project. Also, the 1x1 square rod that was used for the main manifold of the part that you fabricated in the assembly and installation course. It can cause serious damage before becoming visible. So this type of corrosion is quite insidious and difficult to detect. Here's a few examples here. of exfoliation corrosion. Exfoliation corrosion is caused by stress in the part combined with the presence of an electrolyte. 7.1.6 Concentration cell corrosion. Concentration cell appears when two surfaces of the same type of material or metal are subjected to a different concentration of either dissolved oxygen or conductive liquid known as electrolyte. Now in this picture, you can see from the far left debris or protective coating. In this case, we can assume paint, for example. If the paint is lifting, we have an area of limited access of oxygen and an easy access of oxygen where the paint has flaked off, for example. So this will create an anode and cathode portion in the same material, increasing the possibility of concentration cell corrosion. This type of corrosion is close to galvanic corrosion, with the difference that there is corrosion on one or more areas of the same metal part where only the concentration of electrolyte varies. For example here, if a part has a cavity, the water in the cavity stagnates and changes composition as the external water keeps the same composition. Attack occurs where concentration of oxygen or uh, exciting liquid is low, such as overlapping joints soaked in water or exposed to rain. Now, in this case here, high level of oxygen on the outside, that would be the cathode, and the low level of oxygen would be the anode. In this case, it will create a perfect combination for the concentration cell corrosion. Electrolyte or water that will seep in will help in the corrosion or the formation of the corrosion. Often, deposits caused by corrosion block the surface and speed up the process. In the crevice, this corrosion is the result of loss of inhibitor. Loss of oxygen, change or increase in acidity, chloride or sulfate deposition, loss of ions. These are all factors that will contribute to the concentration cell corrosion. Now, if we apply this to aviation, lap joints on an aircraft can be a very high risk for concentration cell corrosion. As you can see here, lap joint modification on a 737 500 series because of problems with corrosion due to concentration cell. Here's another example of a panel or skin panel that was removed from an aircraft, and you can see the gray area is the corroded portion. Now this was replaced during actually it was discovered during an inspection, and the full skin panel had to be replaced. Now if you notice the number of holes in there, these are all rivet holes. So all those rivets had to be removed one by one in order to separate the skin portion from the actual aircraft. Now in this picture here, you can see the rivet heads are lower than the actual skin surface, and this is due to the swelling of the corrosion between the lap joint or inside or between the two sheet metal parts. So this is a sure indication of a concentration cell corrosion. And one of the ways we do the inspection on this is to use a ruler or flat surface in order to verify that the rivets are flush with the skin surface. If there's any, we call it pillowing between the rivets, this will indicate the concentration cell corrosion. 7.1.7 Filiform corrosion. Filiform corrosion is a form of localized omnidirectional corrosion. Omnidirectional meaning it goes in any direction, often associated with aluminum or magnesium that is coated with an organic layer or a layer of paint. It usually appears as very tiny lines under the paint layer. So you can actually see those little lines forming under the paint, and it lifts the paint. So that would be a sure indication of filiform corrosion. This type of corrosion can also be found on other coated metals such as zinc, iron, and steel. Again, you can see those little lines almost look like little trails on the surface of the metal. So this is a sure indication again of filiform corrosion. Generally occurs at high humidity levels over 75% and at temperatures slightly above 23 degrees Celsius. It begins in cracks in the protective layer, again protective layer being paint or varnish, and continues under the layer due to the diffusion of water vapor and oxygen from the air. Here's another good example of filiform corrosion. So you see those tiny lines that look like little trails. So indication of filiform corrosion. 7.1.7 Microbial corrosion. This picture, actually, this is a real picture. Actually, this is in Saint Martin, where the threshold of the runway is few meters away from the beach. You can actually see the planes land there. People gather in that beach to see the planes land and take off. When they do take off, there's also always a risk of incident. If you do a little search on YouTube with the Saint Martin airport, you'll find tons of videos of people getting blasted, jet blasted away from the beach. So microbial corrosion is susceptible on aircraft operating at high temperature and high moisture content. Again, flying in tropical conditions is an issue for aircraft in terms of corrosion. Microbial corrosion is one of them. Microbial corrosion is an issue in fuel tanks. Microbial growth in fuel is triggered by fungal and bacterial growth. Fungus and bacteria have fuel as their primary source of food, and they also prefer kerosene over gasoline because gasoline contains lead to some extent and other elements which can act as poison for the bacteria. Those pictures you see on the bottom is the Titanic, and as you can see, the two main characters from the movie are still there. The condensation of water vapor within the fuel tanks create conditions suitable for microbial growth and contamination within the system. Since fuel and water don't mix, these microbes grow at the fuel water or the fuel/water interface, or where they actually separate, which is usually formed at the bottom of the tanks. Now on the picture you see some brownish residue that's in the bottom of a tank. This will actually be the microbial corrosion or the fungus and that is in the fuel cells or fuel tanks. Microbial growth in fuel is usually described as near to the appearance of chocolate mousse. In severe contaminations, large mats of slime will develop and block filters in the fuel system. Now, obviously, this can be a real issue. One very common fungus that flourishes in fuel is Cladosporium resinae, or clad. Don't memorize this. That's not going to be an exam question. It was first discovered in aviation, where it caused large-scale problems before finally being controlled. So fungus can cause corrosion by retention of moisture on the metal surface. So that's why, again, moisture and metals will corrode. The fungus has the capacity to retain moisture. They are living organisms that often feed on the material on which they grow, mainly the protective film, meaning the paint or the primer or whatever inside the fuel tanks. Their growth occurs at the interface of the water and fuel, meaning where that boundary layer of water and fuel, where they meet, this is where the fungus will grow. Low humidity does not kill them, but slows their growth. They become active again if the aircraft is moved to a dry, from a dry, cold region to a warmer and humid one. So aircraft flying up north are less susceptible to this. Aircraft that are flying in the tropical conditions are more susceptible to that. There are products to detect the presence of bacteria, fungi, and mold in the fuel, as well as fuel additives to remove them. Now, one of them is the BioBor Humbug testing kit. The way it works, a sample of fuel from the tank of the aircraft is injected into a bottle containing the detection liquid. If the liquid becomes pink or red after 24 to 48 hours, it indicates the presence of bacteria. So you need some antibiotics in the tanks to actually kill the bacteria. So if the presence of bacteria or algae are confirmed by the test, antifungal treatment should be used. 7.2 Propitious areas for corrosion. Corrosion can develop anywhere. Some areas are particularly prone to corrosion, for example, on engines, exhausts, and fairings. Exhaust because of the corrosive soot that comes out of the engine, fairings because they are in contact with that, air intake because they can any contaminants can remove the protective layer on the engine intake. On the structure, battery compartments, toilets, and kitchens. Kitchens are called galleys on aircrafts and on ships, actually, on boats. Bilge area. The bilge area is the bottom of the aircraft, landing gear and wheel wells, because they are in contact with the outside elements, stone chips, sand, etc. from the runway. Aileron flap spoilers lodging, where the actual flaps nest, let's say, and the in the wing because it can retain water. Pressure bulkheads, that's the rear of the aircraft. Graphite components or carbon fiber. Control cables, we'll see that when you do the flight controls course. Piano hinges. Piano hinges are the hinges that are often used on aircraft. They're called piano hinges because they're very long length of hinges. We'll discuss that in the coming weeks. And difficult access areas. If you cannot access an area, it is difficult to inspect, and it is difficult to protect. Other locations, spot welding, we'll show examples of that. Engine supports and welded sub-assemblies or assemblies, rotor heads on helicopters, electrical and electronic components or equipment. The most likely places should therefore be periodically cleaned, inspected, and treated against corrosion as necessary. Some high-risk area may require follow-up and more frequent inspections. 7.2.1 Engines. Now, on piston engines or turbine engines, exhaust gas deposits are highly corrosive. Corrosion often develops in the fairing and near the exhaust because of the soot that is expelled from the engine. Soot can be very corrosive and will increase the risk of corrosion. Like in this case here, this is the APU exhaust from the Falcon 20 in the hangar. If you go and look closely at the exhaust stack of the APU, you can see the corrosion on the aluminum skin. Engine air intakes also be monitored because they are exposed to air pollutant, dust, and debris. The metal is often stripped from its protective coating, as I mentioned earlier, so corrosion can develop fairly quickly on engine intakes. Check for traces of moisture, especially on crevices and frames, aluminum and magnesium. Check the condition of the anti-abrasion strips if they are installed. Anti-abrasion strips, it's like basically some sort of a I'm not sure it's vinyl, but it's something that is stick or stuck on the surface, similar to the on cars. Sometimes you have this protective film that is stuck on the hoods to prevent the stone chips. On aircraft, we have something similar that is used. In the battery compartment, the electrolyte vapors of the battery are highly corrosive. When overheating or under load, or even when they're just being recharged, batteries will seep some hydrogen vapors, and hydrogen vapors are highly corrosive. I took this picture of my stepdaughter's car, as she was complaining that the car was hard to start. So I did a little inspection and find out that the positive pole of the battery was badly corroded. So after neutralizing the corrosion and cleaning everything, it went back to normal. Regardless of the coatings, paint or sealants or ventilation, there is always a risk or high risk of corrosion in battery compartments. Corrosion on lead acid batteries is neutralized using a mixture of water and baking soda. Now the recipe, 3 parts baking soda, 1 part of water. Don't memorize this. This is just nice to know if it happens to you. But the baking soda will neutralize acid from the battery. Corrosion on NiCad batteries or nickel cadmium batteries can be neutralized with a solution of either boric acid, ammonia, or vinegar. So remember that for acid batteries we use baking soda, but with NiCad batteries, baking soda will not work. It has to be either ammonia or vinegar or boric acid. When inspecting the batteries, inspect the boxes under the batteries and fume neutralizers and containers. Usually batteries on aircraft, they are encased in some sort of a box, like those 2 examples we have there. These are not the actual batteries, but the containers. and should be inspected inside to verify that there's no corrosion. Here's an example of thermal runaway, meaning overheating batteries that just like run away. They just go crazy, sort of. Uh, it start heating up, and the heat increases until they actually, in some cases, burst out in flames. Here's another example. Now to the left, battery that had suffered a thermal runaway, and on the right, the normal battery. This was on a All Nippon aircraft, uh, All Nippon airline aircraft, a Boeing 787 or Dreamliner. Now you may not remember, but when it was introduced to a service, the Dreamliner had several issues with their battery. In this case here, following the high-profile battery problem caused by the All Nippon Airline emergency landing of a 787 aircraft around the world, all the aircraft were grounded in January 2013 and resumed flight in April of the same year. The FAA authorized the Dreamliner to resume service in April 2013 after modifications were made to their battery system to better control and contain possible battery fires. At this time, we still don't know the exact cause of the battery fires on the 787, and the solution put in place by Boeing may not be able to cover all the possible failures. I didn't do a follow-up on this since I created this course, but it seems like the problem was solved because we haven't heard of a 787 battery fire since then. All right, this takes care of course number 7. Again, questions, you can send them IO. Otherwise, we will talk in the Teams meeting following this this video. So take care, stay safe, and see you soon.